Okay, so today we're going to be looking at recursive functions. So recursive functions are a form of discrete function, and so they give us sequences. They could give us a series as well, but we're only going to work with sequences, so lists of values, lists of terms. So with a recursive function, we get new terms using the previous terms. So what is a recursive function? It's a function where we get new terms in the sequence using previous terms. Okay, so a few things to note. There's no general equation for recursive functions, but there are some notation things that are really important. So let's look at those for now. So t subscript n is term n, and that's the same as has been up until now. So that's the value of term n. Okay, so we have another notation, which is tn minus 1. So that's the value of the previous term to term n. So if n was, say, 5, this would be term 5, and this would be term 4, the term before term 5. So it's the value of the previous term. N minus 1. Also sometimes see n term n plus 1, which is the value of the next term. Term n plus 1. Okay, so let's see how this works. So for our first example, we're going to write out the first 5 terms of our sequence, where t of n is equal to t of n minus 1 plus 3. So what does that mean? That means the term we're trying to find is equal to the term before it, the previous term, plus 3. And it also tells us where term 1 is 5. So if we start writing out our sequence, 5 is term 1. So we already know that one. We only need to find 4 more. And it says, note, we need to know at least one term. So we always need to know one term in order to find the next terms, right? Because that comes back to our definition here, where to get new terms, we have to use previous terms. We have to use at least other terms. So let's see how we can get more terms. So if we want to find term 2, we would plug in n as 2. So let's see what happens when we do that. We get t2 is equal to term 2 minus 1 plus 3. And term 2 is going to be equal to, well, we can do this little algebra. So t1. t1, well, that's just the value of term 1, which is 5. So we'll substitute that in a second. So t2 equals 5, the value of term 1, plus 3 is 8. Okay, 8. Okay, and if we say out this equation, that kind of makes sense. So the value of the term is equal to the value of the previous term plus 3. So 8 is 5 plus 3. That makes sense. So we can see that algebraically through here, and we can kind of say it verbally and understand the intuition that it's the previous term plus 5. So the next one we would expect to be 11, but let's write it out in more detail so we can see that. Term 3 we'd be trying to find is term 3 minus 1 is term 2 plus 3. One thing to note is you have to be a little careful here about your subscript notation, where we have these little labels. and not confusing them for numbers. And the plus 3, we aren't adding that to 2, we're adding it to the value of term 2, which is, in this case, 8. So it's 8 plus 3 is 11. And that makes sense, right? So it's a previous term plus 3. And I think once we kind of get the pattern, we don't need to write out all of the steps every time. For our record keeping, we will write a little bit out. So term 4 is equal to term 3, 11 plus 3 is 14. And the next number, we'd expect to get 17. 5 is equal to the previous term, 14 plus 3, 17. Okay. So there's our sequence. We'll just circle that to denote that that's our response to the question. One thing to note about these recursive functions is, unlike arithmetic or geometric sequence equations, those general equations, we cannot predict far into the future terms. So you may note that this sequence here is arithmetic, plus 3, plus 3, plus 3, plus 3. There's a constant difference. We could write an arithmetic equation for this. And if we had an arithmetic equation, we could answer a question like, what's the value of term 100? We just plug in 100 for n into our general equation, and we could solve for the value of term 100. But here, with a recursive function, in order to find term 100, we need to know what term 99 is. In order to know what term 99 is, we need to know what the previous term to that is, term 98. To know that, we need to know term 97, and so on, and so on, and so on. So these can be very useful, and they'll actually give us patterns we cannot represent using algebra or arithmetic or geometric general equations. But they have some limitations. We can't predict far into the future. I don't know what the value of the 1000th term is unless I were to maybe rewrite a new general arithmetic equation now that I know this is arithmetic. So there are some limitations to recursive functions. All right, let's try another one. This one looks a little bit different. It says find the first 5 terms, again, of the sequence where tn plus 1 is equal to 3tn minus 2. So we could rewrite this if we wanted to as tn equals 3tn minus 1 minus 2. So we could just subtract 1 from both because these are relative to each other. So it's saying the next term is equal to 3 times the current term minus 2. But this is almost saying the same thing. It's like the term is equal to 3 times the previous term minus 2. So this is an option to rewrite it. But the important thing is that we can have either notation, and either notation is fine. Okay, so we know t1 equals 2. So we can start writing our sequence here. So 2. And we want to find term 2. So in this case, n is going to be 1 to find term 2, because we want to know what t2 is. In some ways, I feel like this notation, where we have the tn plus 1 by itself, is a little less intuitive than the first example. But it is a notation that we sometimes see. We have to learn about it. Okay, so that'd be 3 times t1 minus 2. t1, it says, is 2. 3 times 2 minus 2. So that'll be 6 minus 2 is 4. 4. Okay, so term 3, to find that, it's 3 times the term before. 4 minus 2. So that's going to be 3 times 4 is 12, minus 2 is 10. 10. So each time, in order to get the next one, we're tripling and then subtracting 2. So we could probably do that without writing it out every time. But just to show our work, and for our own notes, I'm going to write it out each time. So 3 times 10 is 2. So that's 30 minus 2 is 28. Last one, now we're getting some big numbers. Be a little more challenged. Term 5 is going to be 3 times term 4. 28. It's 2. That's a little harder. That's 84 minus 2 is 82. Okay. There's our equation. Now, if we take a second here and we look, is this arithmetic or geometric? Well, if it's arithmetic, it goes plus 2 plus 6. That doesn't work, right? It has to be constant difference. If it's geometric, it has to be constant multiplication. This is times 2 times like 2.5 times 2.8 times I don't even know. But it's not a constant multiplication either. So this is neither. And that's one of the useful things about recursive functions is that we can represent non-arithmetic or geometric patterns in numbers. So there we go. Okay, so here's another part to this question where it says, what about if instead of t1 being 2, it was 1? Okay, well, let's see how that changes things here. So if we would have 1, and then to find term 2, we have 3 times term 1, the value of term 1, which is 1, oops, minus 2. That is going to be 3 minus 2 is 1. We get value of term 2 is 1. Okay. So wait a second. If that's true, then when we find term 3, we're just going to get the same thing, aren't we? 3, the value of term 2 is 1 times 3 minus 2 is 1 again. So it seems like we just keep getting 1s over and over and over again. Right? So it's really important that the starting value really can change what our equation looks like. Right? This is a very simple sequence. This is just a list of 1s. Right? So that's interesting that the starting value can drastically change things. And if we started with a negative, we could think about what would happen, right? It would get negative really fast. Be interesting. Okay. Let's look at the next one here. So this time we want to write a recursive function for the sequence 1, 3, 7, 15, 31. Okay. So this is perhaps the more challenging thing because there is not necessarily a straightforward technique, strategy, or process to find the recursive function sequence for a sequence. And so you just kind of have to like try things until you figure out a pattern that works and then write it algebraically. So I'll kind of walk through this one and walk through kind of my thought process. So the first thing I would want to do is see if it's arithmetic or geometric, because then it's just plus, the previous term plus something, the previous term plus something. Right, that would be a good arithmetic, or the previous term times something. That would be geometric. So it's plus 2 plus 4 plus 8. Yeah, that's not working. So this is not arithmetic, so there's not a constant addition happening from one term to the next. What about multiplication? So that's times 3 times something weird times something else weird. Okay, well, that doesn't seem to work either. There's not a constant multiplication. But maybe we can come up with some sort of combination of those two. And usually, for our purposes in this course, it'll be something, or probably be something like that. There are, in fact, several solutions to this question. There are several different recursive functions that will give us this 5-number pattern. But there's one or two easier ones to find. So let's start by trying. So there's so many ways to go from 1 to 3, right? We could add 2 times 3. We could, do times 4 minus 1, things like that. There's so many ways. Sometimes it's easier to look at some of the bigger numbers a little bit. So let's go from 3 to 7. Well, I could triple it and subtract 2. And if that works, it has to work for the next one. Triple subtract 2. So that'd be triple would be of 7 would be 21 minus 2 is 19, and that doesn't work. Okay. And maybe by now some of you have seen what the pattern is. But what if I instead double it to 6 and then add 1 to get to 7? So that'd be that would work, right? So 3 times 2 plus 1 is 7. What about 7? Double of 7 is 14 plus 1 is 15. Well, it seems to be working, but we should check with all the numbers to make sure it works. So 15 times 2 is 30, plus 1 is 31. So it seems to work. And what about 1 to 3? Does that work? Double of 1 is 2, plus 1 is 3. So it seems to work. So now we have to try to represent it with an equation. So the new term, Tn, is going to be 2 times the previous term plus 1. So, and if you want, you can fill in a couple of values. Right? So that's our recursive function. And we might also want to say what our starting value is, where T1 is 1. Right? We need, like, we have this is the recursive function, but it's also nice to have that starting value in there. So that way we could reproduce. If we just knew this part in purple here, we could reproduce this sequence because we know the starting point. Okay, so there's another thing that can happen in our equations that we can see in this last example here. And that is where we have an n value in the equation. So this is our new term is the previous term plus n. So this is an example where the actual value of n is important to finding the term number. Let's see what happens to our pattern. So it says T1 is 1. So let's start writing our sequence here. 1. Let's try to find term 2. So here n is 2. So that's T2 minus 1, term 1, plus n. N for this is 2. So that's going to be value of term 1 is 1 plus 2. And we get T2 is 3. The value of the third term is 3. Find term 3. It's going to be the value of the previous term, term 2, plus n. So n is 3 for this question. So that's going to be T2 was also 3. So 3 plus 3 is 6. Okay, term 4 is the value of term 3 plus 4, value of n, our equation here. So it's going to be 6 plus 4 is 10. And T5 is going to be the value of T4 plus n. It's 5. 10 plus 5 is 15. That is our sequence. And if we look at it, we can see it goes plus 2, plus 3, plus 4, plus 5. Right? And we can see that increasing addition that's happening by our n value going up by 1 each time. All right. That's it for the lesson on recursive functions.